Hi everyone, welcome to this YouTube channel. At this point, we're going to look at WAEC 2025 Physics Theory questions. Some questions from WAEC 2025 Physics Theory. So we'll start with number 12, part 2 or session 2. Number 12 question there. So we'll go to the question and then we'll go to the solutions. 12AI says, state two similarities associated with alpha, beta, and gamma rays. State two similarities associated with alpha, beta, and gamma rays. Solution 1. They are all forms of nuclear radiations emitted by unstable nuclei. 2. They can all ionize matter, although in different extents. 12AI says define natural radioactivity. Define natural radioactivity. Natural radioactivity is the spontaneous emission of radiations in bracket alpha, beta, and gamma rays from the nuclei of unstable atoms found in nature. 12A write a general equation for alpha decay, beta decay, and gamma decay, where S is the parent nucleus and Y represents the daughter nuclei respectively. The solution for alpha decay is have S subscript A, that's the mass number, superscript A, the mass number, and then Z, that weak number, giving us the product Y, superscript A minus 4, subscript Z minus 2 plus alpha. For beta decay, you have A subscript A, subscript A, the superscript A, the mass number A, and then subscript Z, giving us Y superscript A subscript Z plus 1 plus beta. Then for gamma decay, you have S superscript A subscript Z, giving us S superscript A subscript Z plus Y. So these are the solutions. 12AIV says, mention one example of natural radioactivity. Mention one example of natural radioactivity. Solution, spontaneous emission of an alpha particle by uranium, that's U, capital U, 235, to produce thorium, that's TH, 231. Spontaneous emission of an alpha particle by uranium 235 to produce thorium 231. Question 12BI. A kinetic energy of 1.80 10⁻⁻⁶ joules is possessed by an electron ejected from the surface of a metal when the surface is illuminated with light. If the work function of the metal is 1.20 10⁻⁶ joules, calculate the frequency of the incident photon. In bracket, C, speed of radiation is 3.0 per 8 meter per second. Planck constant H equal to 6.6 per minus 34 joule second. Solution, 12BI. The kinetic energy of the J electron is 1.80 per minus 16 joules. The work function is 1.0 per minus 16 joules. Then the relationship between energy of photon, work function, and kinetic energy given by the Einstein equation, giving us E equal to W plus KE. So add up E equal to 1.20 per minus 16 plus 1.80 per minus 16. That will give us E equal to 3.0 per minus 16 joules. And E is HF, L becomes E over H. Substituting, you now have 3.0 per minus 16 all over 6.6 per minus 34, and that will give approximately 4.55 per minus 17 Hz at the frequency. II says, state two characteristics of a cathode ray tube. 1. It contains a vacuum tube in which Electrons are emitted from a heated cathode and accelerated towards a fluorescence screen. Then, 2, the electron beam can be deflected by electric or magnetic fields to create images or patterns on the screen. 12Ci. Given that 13 superscript 5 subscript, that the mass number, atomic number G, undergoes an alpha decay, I write an equation to representing the process. I identify the daughter nuclei. So equation for the process again as the I, 12Ci, G superscript 13, mass number 13, subscript 5, number 5, giving us lithium, Li, superscript 9, mass number 9, the atomic number subscript 3, plus 42He, that is alpha. The number 2, identify the daughter nuclei. Daughter nuclide is lithium-9 isotope. Daughter nuclide is lithium-9 isotope. So we are done with number 12 so far. So good. We'll go to number 10 in same part 2. Number 10A, the first question says, define the following wave terms. I, first overtone. I, end correction. Solution 10AI. First overtone is the second lowest frequency produced by a vibrating object or system. It is the first frequency above the fundamental frequency. I repeat, first overtone is the second lowest frequency produced by a vibrating object or system. It is the first frequency above the fundamental frequency. 10AII, end correction is a small additional length that must be added to the physical length of an open pipe or tube to account for the effect of the air vibrating just outside its open end. Repeat, end correction is the small additional length that must be added to the physical length of an open pipe or tube to account for the effect of the air vibrating just outside its open end. Question 10b. A 40 cm tube closed at one end resonates at its fundamental frequency with a tuning fork of unknown frequency. If the end correction of the tube is 3.2 cm, determine the frequency of the fork. Bracket, velocity of sound in air is 330 meters per second. To solve it, we first of all convert the length of the tube, 40 cm to meters, divide by 100. 40 cm gives us 0.40 meter. The end correction is 3.2 cm. Convert to meters, divide by 100, that gives you 0.032 meters. Then the effective length will now become LEFF, will become the length of the tube plus the end correction. That is going to be 0.40 plus 0.032, and that will give us 0.432 meters. Then wavelength is given by, for a closed pipe, given by 4 times length, effective length, that gives us 4 times 0.432, that gives us 1.728 meters. Move, velocity is frequency times wavelength. So frequency becomes velocity over wavelength, substitute. Velocity given in the equation, 330 all over wavelength, calculated above 1.728, that gives us 190.97 Hz, approximately 191 Hz as the final answer to this question. 10CI says Two plane mirrors are inclined at an angle beta to each other. An object placed between them formed 8 images. At what angle are the mirrors inclined? Two plane mirrors are inclined at an angle beta to each other. An object placed between them formed 8 images. At what angle are the mirrors inclined? So solving this, n is 8, number of images. Theta, the angle is beta. Then the formula for two inclined mirrors given by n equal to 3 over theta minus 1. So making n the subject, or crossing 1 over to the left-hand side, we'll now have n plus 1 equal to 3 over theta. Then making theta the subject, theta now becomes 360 all over n plus 1. And your n is 8. Substituting, we'll now have 360 over all over 8 plus 1. That is 360 over 9. So 360 over 9 gives us 40 degrees. So theta, which is equivalent to beta, is now 40 degrees as our answer. Look at 10 CII. That says an aluminium metal is illuminated with light of wavelength 3.0 to power minus 7 meters. If the kinetic energy of the electron emitted is 1.5 to power minus 19 joules, calculate the 1. Maximum velocity of the photoelectrons, 2. Work function of the metal, in bracket, speed of radiation is 3.0 to power minus 8 meter per second. ME, which is the mass of electron, is 9.1 to power minus 31 kilogram. And then the Planck constant is 6.6 to power minus 34 joule second. So to solve the 10 CII, that the value is given to us, we dictate them from the equation. Wavelength is 3.0 power minus 7 meters. Speed of radiation, C, is 3.0 to the power 8 meter per second. Planck constant 6.6 power minus 34 joule second. Then the kinetic energy of the photoelectrons is given by 1.5 power minus 19 joules. So go to the I part of it, 10 CII, capital I. So to find the velocity of the electron, we equate Ke to be equal to half mv squared. So you make the formula V now becomes equal to 2Ke over m, square root of 2Ke over m. We substitute, we now have square root of 2 times 1.5 to the power minus 19 all over 9.1 to the power minus 31. So solving that inside the square root, we now have V equal to 3.297 to the power 11. So find the square root of what's inside the bracket, we now have 5.74 times the power 5 meter per second. So this is the speed of the electron, the velocity of the electrons or the photoelectrons. The same number, question II, says the work function of the metal. To find work function, we'll first of all find the energy of incident radiation using the Planck formula, E equal to Hc over lambda. Substitute, we now have 6.6 power minus 34 times 3 times 10 to the power 8 all over 3 to the power minus 7. Solving for the energy of radiation, we now have 6.6 to the power minus 19 joules. Then from Planck-Einstein equation, E equal to W, work function plus kinetic energy. So making the work function the subject, work function now becomes E minus Ke. We now substitute the values. So the work function now becomes the energy of radiation 6.6 power minus 19 minus the kinetic energy given to us, which is 1.5 power minus 19. So we'll now factorize W equal to 6.6 in bracket minus 1.5, bracket closes, power minus 19, and that will give us 5.1 times power minus 19. So this is now the work function, 5.1 times power minus 19, the work function of the metal. 10D says define stopping potential. Stopping potential is the minimum retarding potential applied to a metal plate in a photoelectric experiment that stops the most energetic photoelectrons from reaching the collector. Stone potential is the minimum retarding potential applied to a metal plate in a photoelectric experiment that stops the most energetic photoelectron from reaching the collector. So we are done with number 10. So that's one question in part 2. We'll now go to number 9, and that question in part 2. So move to question 9a. State one difference between deformation and elasticity. One difference between deformation and elasticity. Solution. Deformation refers to the change in shape or size of an object due to applied force, while elasticity is the property of a material that allows it to return to its original shape after the force is removed. Deformation refers to the change in shape or size of an object due to applied force, while elasticity is the property of material that allows it to return to its original shape after the force is removed. 9b. The following results were obtained from an experiment performed on a spiral spring. The stretch force and in Newton, the extension in centimeter. Force of 0.0 goes with extension of 0.0. Force of 1.0 introduce or produce extension of 5.0. Force of 2.0 gave us extension of 10.0. Force of 3.0 gave us extension of 15.0. Force of 4.0 Newton gave us extension of 20.0. Force of 5.0 gave us extension of 25.0. Force of 6.0 gave us extension of 30.0. So the first question, 9b, says plot a graph of force against extension. So you have a graph of force on the vertical axis against extension on the horizontal axis. Extension in centimeter, E in cm, and force in Newton. Look at the scale. The midpoint is 0, the point intersection is 0, and then on the vertical axis, we have to choose a bus for 1 unit, and the bus is 2 cm. So 2 centimeter for 1 unit, or 1 Newton on the vertical axis. So 2 centimeter from 1 unit, you can have 1, 2, 3, 4, 5, 6, up to 7. Then on the horizontal axis, where you have extension, we choose a bus, which is 2 cm for 5 units. You have 5, 10, 15, 20, 25, 30. And we produce a perfect straight line graph. Then we took our slope, the slope between the second point and the last point. See the triangle there for our slope. The intercept on the vertical axis for the on the first axis 60, the upper one for the slope, and then 20, the lower force. Then we go down for the extension, we have 30, and then we have 30 and then 10. So let's go back to the solution. 9b, I say determine the slope of the graph. So the slope is given as change on force axis all over change on the extension axis. So delta F over delta E equal to 6 minus 2 Newton all over 30 minus 10 centimeter. So that gives us 4 Newton all over 20 cm. Convert the 20 cm to meter, divide by 100, that gives you 0.2 meter. So divide 4 by 0.2, that gives you 20 Newton per meter. So that is our slope for this graph. 9b triple I says, what does the slope of the graph represent? What does the slope of the graph represent? Solution 9b triple I, the slope represents the elastic constant or the stiffness of the spring. Elastic constant or the stiffness of the spring. Number 9c, a rubber gun is used to project a stone of mass 40 grams. If the rubber of the gun has an elastic constant of 350 Newton per meter and was stretched 4 centimeter, calculate the stone speed of projection. Repeat, Rubber gun is used to project a stone of mass 40 grams. If the rubber of the gun has an elastic constant 350 Newton per meter and was stretched 4 cm, calculate the stone's speed of projection. Solution will first of all convert the values to standard units. Mass of the stone 40 grams, convert to kg divided by 1000, that gives you 0.04 kg. The elastic constant is 350 Newton per meter. The extension is 4 cm, convert to meter divided by 100, that gives you 0.04 meters. Then energy being conserved, the elastic potential energy will now become equal to the kinetic energy. So we'll now say half Ke squared equal to half mv squared. So half cancels half. We'll now have Ke squared equal to mv squared. We make v the subject. V becomes square root of Ke squared all over m. Substitute the values. K is 350, E is 0.04, and also m the same 0.04. So solving the values in the square root, we'll have v equal to square root of 14, and that gives us the final answer, which is 3.74 meter per second. 9D is a define bulk modulus. Bulk modulus is a measure of a material's resistance to uniform compression. Bulk modulus is a measure of a material's resistance to uniform compression. 9DII. A vertical wire is suspended from a support with a mass of 2.5 grams attached to the free end to stretch the wire. If the load on the wire extends it by 2 cm, determine the energy gained by the wire. Take your G or acceleration as 10 meters per second squared. Solution. So convert the mass to kilogram, 2.5 gram divided by 1000, that gives us 0.0025 kilogram. Our acceleration of the graph is given to us at 10 meter per second squared. Extension, which is S, is 2 cm, convert to meter divided by 100, has 0.02 meters. The weight or the force due to gravity is mg, which is the mass, 0.0025 times 10, that gives us 0.025 Newton. Then the elastic potential energy of the body is given by half Fs, where S is extension. That becomes half times 0.025, which is our force due to gravity or the weight, times the extension, which is 0.02, and that gives us 0.0025 joules. So that the energy answer is 0.00025 joules, or in standard form 2.5 times power minus 4 joules. So we are done with session 2. We have done 3 good questions. We'll now go to part 1 and take 4 questions from part 1. So we're on to part 1. The first question there says, a missile is launched vertically upwards with the initial velocity u at an angle theta to the horizontal. Capital R, often referred to as the range, which is represented by the expression capital R equal to u squared sine 2 theta over g. Determine the dimension of R. Solution. Dimension for velocity, u is the initial velocity, is L, capital L, t bar 1, t raised to power minus 1. You know that L is the length and capital T is time. The dimension for acceleration is L, capital T raised to power minus 2. Sin theta in that formula for range is dimensionless, has no dimension. So range now becomes u, which is dimension of, you have that absolute value L, capital L, T raised to power minus 1, all squared. But the formula of a range, u is squared all over. Under it, you have g, and g is, you have the absolute value L, T raised to power minus 2. So when you simplify that, you're going to get L at the dimension of range. L, dimension of range. And of course, that is actually correct because range represents distance. So dimension should also be L. Number 2 says, state one use of I, gas laser, B, chemical laser, and I, dye laser. Gas laser, it is applied in the industry for cutting, welding, and engraving. Also used in medical applications like skin resurfacing and eye surgery. Chemical laser, it is used in military applications, particularly for directed energy weapons and in research for high power laser systems. Dye laser, used in spectroscopy, that's chemistry, and biomedical research, and so on. Going to number 5. Number 5, a curve of natural length 5 meters was extended by 0.04 meters when a force of 6 Newton was applied. What would be the new length when a force of 8 Newton is applied? Solution: the original length LO is 5 meters. The first extension produced E1 0.04 meter. We're looking for the second extension E2. The first force F1 6 Newton, second force F2 8 Newton. Applying that principle from Hooke's law, F1 over F2 equal to E1 over E2, making E2 the subject. E2 becomes F2 times E1 all over F1. Substituting, E2 becomes 8 times 0.04 all over 6. That gives us 0.0533 meters. Then the new length should now be original length plus the new extension LO plus E2. That becomes 5 plus 0.0533, and that gives us 5.0533 meters, approximately 5.05 meters. Number 4, a satellite orbits the Earth with a velocity of 5.8 km per second. The period of the satellite in the orbit is 20.2 hours. How high above the Earth is the satellite? Take radius of the Earth as 6,400 kilometers, mass of the Earth as 5.97 × 10^24 kg, then pi 3.14, then the gravitational constant 6.67 per minus 11 in SI unit. So solving number 4, the velocity given to us is 5.8 km per second. Converted to SI unit, multiplied by 1,000, you have 5,800 meters per second. The period is 20.2 hours, convert to seconds, multiplied by 3,600, that gives us 72,720 seconds. Apply the relationship period equal to 2 pi root r cube all over g times me, mass of the Earth, that's the me. Making r cube the subject, r cube becomes equal to t period squared times g times me all over 4 pi squared. Substituting re becomes 72720 all squared times 6.67 to the power minus 11 times 5.97 to the power 24 all over 4 times 3.14, that is in brackets squared. So our RE becomes 5.34 times 10 to the power 22 meter cube. R becomes the cube root of 5.34 to the power 22, and that will give us 3.70 to the power 7 meters. The height we're looking for is now the R minus radius of the Earth, which is 3.70 to the power 7 minus 6.4 power to the power 6. And that will give us 30,600,000 meters, which is equivalent to 30,600 kilometers as our answer. So thank you for staying connected. Share the video to somebody in need that can be able to go through this and then understand the concepts of physics. Thank you very much.